All right, and welcome to the normal model. We have made it from discrete to continuous. In the past, we were looking at discrete random variables most of the time. Specifically, we talked about the binomial distribution. Binomial distribution was great for if we had repeated trials that always had the same probability. We could think of the probability as what percent of the area is underneath each of these bars. So probability that x is between 8 and 12 is this relative area. Now, we're going to be moving back to continuous random variables, which work very similar, but the problem is now we just can't count because the whole thing about continuous is that there's infinitely many values, right? There's no little pieces that we can add up together. We'd have to add up infinitely many pieces, but the area concept for probability is still the same. The more area, like as I expand this area, make this area bigger, this probability goes up. Bigger the area, the bigger the probability. If we make that area smaller, the probability goes down. Okay, so we can think of area and probability the same, or at least similarly, unless we really want to get into the back end, as for the discrete case. So we're dealing with continuous random variables here. Not going to talk too much about them, just kind of introducing really roughly, this is what we're doing now. So what we are actually going to get started with is the normal model, all right, also called the Gaussian distribution. Now, the normal distribution is very common. It's normal to see in nature, okay? It's the bell curve. We've seen it. You've seen this before for sure. Because so many things in life are normal, like people's heights, people's weights, IQ, if you care about IQ, distribution of like weather patterns and stuff like this. And there's way more that can be said about the normal distribution that is way outside the scale of this class, but it pops up in so many places. This is by far the single most important distribution we're going to be talking about in this class. So kind of like we have been doing a lot of things in this class, we're really going to introduce it with some examples, okay? And just kind of not spend too much time on definitions and more introduce terms as they kind of appear. So let's start by looking at an example. So we're looking at the annual rainfall in Portland, which is less than Olympia, Washington. But anyway, the mean annual rainfall in Portland is unimodal. Unimodal means there's one mode, there's one big kind of hump. Remember, like bimodal was something that, maybe it's something like this would be an example of something that's bimodal. But here we have something that's unimodal. There's one really significant hump or peak. It's unimodal and approximately symmetric with a mean of 40 inches and a standard deviation of 8 inches, rounded to the nearest inch. So label the normal distribution model for this situation. All right, so there's a lot going on here. First off, this is how we write it. X is normally distributed. That's what that N means. With mean 40 inches. And again, sometimes we'll write mean as the Greek letter mu. And standard deviation, 8 inches. Okay, this is kind of some notation that we're going to do here. So the mean is the average. Mean is the average. So if we're labeling this graph, where's the average? The average is right down the middle in this case. In this case, since it's perfectly symmetric, the average, the mean, and the median are identical. This is our mean right here. Our mean is the center. It's going to be 40 inches of rainfall. Let's label inches of rainfall. Okay. Now, the way that standard deviation works, and again, we've calculated standard deviations before, but for normal models, standard deviations are even more powerful. Okay. We mentioned that standard deviation is very, very useful for symmetric data, whereas IQR, interquartile range, is more useful for asymmetric data or skewed data. Well, we have symmetric data here, and this standard deviation is going to be very powerful. Specifically because all normal models look the same, they just have different scales. So what we're going to do next is we're going to say this is 1 standard deviation above the mean. This is 2 standard deviations above the mean, and this is 3 standard deviations above the mean, and we can reuse this graph for anything that's normally distributed. Okay, so this is 1 standard deviation above the mean, that's going to be 48. Again, that's like a side note, right? 48, that's 40, which is mu, plus 1 times sigma. That's the mean, plus 1 standard deviation. Let's add another standard deviation. That's going to be another 8. This will be 56. Another standard deviation, that'll be 64. And let's do it in the other way. Subtract 8s as well. This is how normal distributions look like. So within 1 standard deviation of the mean, which is a phrase that comes up all the time, let's say, how much of this data is within 1 standard deviation of the mean? Well, we would look and say, this is all the data that's in 1 standard deviation of the mean. This is quite a bit. If you think about total area, this is quite a bit of the total area. Within 2 standard deviations of the mean, that would be between 56 inches and 24 inches. Within 2 standard deviations of the mean, that is a lot of data. That's almost everything. And within 3 standard deviations, if we went to 64 and 16, we'd get really, really almost everything. Okay, so we've labeled everything. We've kind of conceptually thought about what a standard deviation looks like for a normal distribution. And that really does bring us into this next rule. It's called the empirical rule. And this says that in a normal model, so think about this graph that we filled in a normal model, about 68% of the values fall within 1 standard deviation of the mean. And again, that corresponded to this situation. 68% is about that. It also says that 95% fall within 2 standard deviations of the mean, which we also showed. 95% would be everything in here, which is almost everything. And within 3 standard deviations of the mean, it's 99.7% of the data about. Okay. So it wants us to label the bell curve above to show these key features. So 90, how should we do this? We should color code it. Let's say that's, this is 68% of the data. So within these gray bars. No, gray is not good. Let's label it a better color. Let's say 68% of the data is within the red bars. 68% approximately is it within the red bars. Let's say 95% is within the blue bars. And the last color, let's say, what color do I want that's different enough? White. Yeah, that'd be a great choice. I don't know, black. 99.7% within the black. All right, and you can even see on this little graph, right? It doesn't even look like there's anything outside of the black. And there is, just 0.3%, so not very much. Okay, this is the empirical rule. The book does something a little silly, right? It calls it the 68, 95, 99.7% rule. And some people do that, but it's quite a mouthful, right? 68, 95, 99.7% rule. How many syllables is that? 68, 95, 99.7% rule. That's 14 syllables. That's too much. It's also called the empirical rule. Okay. That's what I think most people call it. But calling it the 68, 95, 99.7% rule is very useful for remembering it, right? If we're always calling it that, then whoa, when I move the pen real fast, it disappears. Magic trick. All right. Oh, yeah, there we go. A value that's more than 2 standard deviations away from the mean is considered unusual, or an outlier maybe. If it's more than 3 standard deviations from the mean, it's very rare, and specifically very rare that it's almost impossible. Keyword is almost. It's almost impossible. All right. And again, if we're kind of looking at this graph below, the mean is always right here. And then this is within 1 standard deviation of the mean. That's the mean plus sigma. Within 2 standard deviations of mean, that's 2 sigma. And within 3 standard deviations of the mean would be mu plus 3 sigma. And you can do the same thing on the other side, right? U minus 1 sigma, mu minus 2 sigma, and mu minus 3 sigma. So this is what all normal graphs look like. The only difference is plug and play. You're going to have different means. You're going to have different standard deviations, but this is what they always look like. All right. And that is our empirical rule. All right. So now you can have a little fun with this. This is 68, 95, 99.7% rule. How are you going to remember that? One way is with music. We can think about these as intervals, as what tones they are, right? If we're looking at a C major scale, right, the 6th is an A. So 68, that's like A, C, the 6th, the 8th, yeah. So the 68, 95, 99.7% rule, this is what it sounds like. 6, 8, 95, 99.7. Listen to that. This is the empirical rule. This is what the empirical rule sounds like. 6, 8, 9, 5, 99.7. So you can get that little tune stuck in your head. It's even better if you end on a C, right? Nobody wants to end on the 7th. There we go. maybe if we use that, I'll chime it out for you again. All right, so let's finish up this video. Let's use the empirical rule. So let's do an example. To find a percentage using the normal model, draw and label the model. So we're going to start by doing what we did in the last one. Draw and label the model. Shade the area or percentage that you want to find. This is a good visual way of connecting information. Okay, so in our case, the mean is 40 with a standard deviation of 8. So again, on all of these, let's just jump right into this. On all of these, we're going to label them the same way. So this is kind of a good thing for you to do. Feel free to just kind of take a little bit of time. Let's just label all of these graphs that we're going to do before we even start. That's our empirical rule right there. Or you can even do that in solfege if you want. Any solfege fans? And go la do re sol re re ti do. There we go. Yeah. All right. That's enough singing for today. But don't worry, the piano's going to come back. All right, so we have all of these labeled. They're all labeled the same way. Let's go through them. Part A. What percentage of the time is the annual rainfall between 32 and 48 inches? When is it between 32 and 48 inches? Well, this percent of the time. That's within 1 standard deviation of the mean, right? Within 1 standard deviation of the mean. Well, what's the empirical rule? The empirical rule is all right, it's 68, 95, 99.7. So 68% is within 1 standard deviation of the mean. Okay. And we'll calculate it exactly later. But this is how we can use the empirical rule. Just if you know that something is even kind of close to normally distributed, then you can use that as like a gut check or like a head thought of what kind of size are we looking at. I think like IQ is another example that people like to talk about a lot. IQ is stupid, by the way, but that's a rant for another time. I think so. The average IQ, I think, is 100, and then a standard deviation is 10. So between 90 and 110 IQ would be 68% of people, approximately. But I'm not going to get started as an IQ, but it's a good example because a lot of people are familiar with it. What's the probability that it's more than 48 degrees? There was a cat hair. Well, here's 48 degrees. The probability that we're more than 48 is everything to the right of 48. Unfortunately, we don't have, the empirical rule doesn't include anything about what's outside, what's higher than 1 standard deviation, but we can figure out the answer, right? This blue, right? This blue is exactly this red area. But notice this red area is the same as this red area. It's symmetric. So this blue, what's the relationship between, because we know what this red is, right? I know what this total red area is. Probabilities have to add up to 100%. So this red area is about 100% minus 68%, or 32%. Ah. Well, what's the relationship between this blue area and this red area? It's half. This blue area, whoa, wrong button, is half of the red area. Well, so this blue area is about 16%. About 16% of the data is above 1 standard deviation of the mean. All right. Let's do part C. When is it 24 or less? When is it 24 or less? Well, we're going to do the same thing. All right, let's approach it in steps. Well, we can start by looking at the red area. All right. This red area, right, the blue area is going to be half. Hold on, Jason. This graph is not working out for you. All right, look at this in steps. Because this is asking about when are we less than 2 standard deviations of the mean. All right, maybe write that. All right, less than 2 standard deviations, or lower than, less than implies distance, smaller than the mean minus 2 standard deviations. We can do it in steps, right? Within 2 standard deviations of the mean, we can use our empirical rule. Dum, 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 dum. That only helps if you know, that only helps if you know a lot of music. Otherwise, you're just going to have random notes stuck in your head for no reason. It's the 68, dum, dum. Wait, that was a fourth. Never mind. Imagine a minor third instead. 68, 95, 99.7. That's the empirical rule. So this is the 95%. So what's outside of that 95% is 5%. And we only want the left half of that. So you just kind of problem solve procedurally, like go through in order. So then what we actually want, right, is we only want this left piece. That's going to be half of that. I was going to color code my answer, but I ended up just doing it all in red. but that's okay. All right. So we're less than 24 inches in Portland, only 2.5% of the time. It's very rare that Portland's going to get less than 24 inches of rain in a year. Very rare. Even more rare for us up here in Olympia. What's the probability that it's 54 or less? I have no idea. 54, that's like here. All right, well, that has nothing to do with standard deviations, right? This is going to be a slightly smaller probability than within like less than 56. We're going to have to guess twice. So we can guess right now. But the empirical rule, the 68, 95, 99.7% rule doesn't help us. That's where the next video is going to come into play. How to calculate this with a computer. We're not going to be doing it by hand. By hand is not really possible. All right. So we have to use computers for this sort of thing. All right. And that's the video. That's everything related to math. Dum, 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 dum. That's everything related to music. And I'm going to end this video with something that's very sad to me that doesn't involve you. My neighbors at my apartment complex, they moved out and the floor is getting redone. And I just heard the people come, and on Friday they came, and it was so loud, such loud hammering for literally over 6 hours. And they just got here. I know it's going to happen again. I'm going to be losing my mind in the next couple of videos. So stick with me. Good luck with your math, and bye-bye.